Alright, here we go, guys. We're going to talk about states of matter and different phase changes. So we're talking about the three main states of matter: solids, liquids, and gases. There's technically two or three more depending how you look at it. Really, really cold, there's Bose-Einstein condensates. We're not going to talk about those. And plasma. There's also probably a time crystal thing that was just discovered, but I don't know much about it. Alright, so the main one, solids. Most common one we talk about is ice. We'll use water as our main example. This is the state of matter that's got the particles in the most locked together state. They cannot move. They are stuck together by strong attractions between the molecules. We often call them bonds, but they're not technically bonds. So they are stuck in one set pattern. So on the left, this picture shows the water molecules attracted to each other in one set location, which spreads out the water molecules, which is why it makes water more voluminous. It's not a real word. Having more volume, which makes it less dense, which is why water floats as a solid, which is an uncommon property. It allows us to live with water being our main liquid. Liquids, on the other hand, they're still attracted to each other, still those attractions. However, they have enough energy in them that now they're bouncing around, and that movement means they take the shape of the container, and they are higher energy, but they're still sticking to each other, but they stick and move around at the same time. To get from a solid to a liquid, you need to add energy, add heat. You need to break those attractions, those bonds between the particles here. So those things have to be, enough energy has to go into these guys to make them break and move into, so they can all be vibrating on their own, moving around in a liquid form. Now you go from liquids to gases, where they're all free-flowing, and they can pretty much ignore the attraction between water molecules. They have to get a lot more energy. All the attractions between the water molecules in the liquid state has to be completely vibrating so much that they can then separate then free-flying gas particles to make it into steam. So they're moving so fast, they don't feel the attraction between them. This one will take up the most space if you have the same amount of particles as you would in the liquid. So a mole of water in the liquid state versus a mole of water in the gas state, steam. The steam is going to take up way more space. It'll be farther apart because there's more energy in them. Alright, so what happens to a substance during a phase change? Well, as water heats up, some of the particles, the temperature goes up, some of those particles get more energy. On average, they're all going to get more energy, but we said temperature is just the average amount of kinetic energy. So some have more, some have less. We take the average as the current temperature. So we say the temperature is 95 degrees Celsius. Some are at 95, some are at 96, 97, 98, 99, some are at 90. So the ones that are cooler, closer to 90, are down here. They don't get to boil because boiling is 100 degrees Celsius. Ones that are at 100 have enough energy, they can go up and they'll get to the boiling point. If they have enough, they'll break free and they'll then be free enough to fly around as gas particles. The ones lower than that are going to stay down as a liquid because their attractions are stronger to stick to each other. Then they have energy to break apart and fly as separate gas particles. I think that's what I just said. Yep. Same idea when you go from a solid to a liquid. There's enough energy in there, it can break that loose bond and then make it vibrate around. If not, it's going to stay in a solid phase along the way. When you're going from a solid to a liquid, you have to break all of those attractions before you can start heating up again. We'll look at that again in a minute. If you need to pause and write this down, go for it. If not, I'm going to move on. Okay, so see the three separate solid, liquid, gas phases of water here. Down below here we have a phase changing chart. So they've got them all color coordinated for what I've got up on the top right. If we look at the very bottom of this, it's the lowest temperature and also the lowest amount of heat has gone into it. So in our blue segment, there's no heat energy in there yet. But as we add heat energy to solid, in this case we'll use water as an example. This will work for any substance. So as we add energy to it, it's going to heat up the solid. It gets warmer, 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 warmer. Eventually we get to the freezing or melting point. That's where the blue meets the green. So when it gets to that point, now all the energy we're putting into it is not going to raise the temperature. All that energy is going into taking those locked into atoms that are here, and energy is going to breaking them apart so that they can then vibrate around each other. They can act as a liquid again. As you're going to do that, all the energy is going into breaking those bonds until all of them are broken. When they're all broken, we've gotten to this point, and we now have all of the solid turned into a liquid. All that energy is turned the solid into liquid. Once that happens, then all the energy we're putting in goes back into heating up the liquid and making the liquid warmer. In water's case, from 0 degrees all the way up to 100 degrees Celsius. Then at 100 degrees Celsius, we have to go from a liquid, those vibrating particles, and give them enough energy to break off and become steam and go flying around as steam particles. And that's also going to take energy, but it doesn't get warmer when that happens. It just takes energy to have them break apart from the attraction between the other particles. So then that's why the energy going into it here goes energy in, but no temperature up. There's no increase vertically as the energy goes into it. It's just making them go from liquid to gas. Once they're all gas particles, then it goes back up and starts making the steam hotter. From 100 degrees Celsius up to whatever. Technically, eventually, if you got the plasma way up here, it would eventually phase out again, but we're not going to do that. That's an insane temperature. Okay, so let's look at an example problem. If the question was how much energy is needed to heat 150 grams of water from negative 15 degrees Celsius to 125 degrees Celsius. So look in the chart and see, all right, first we gotta know where's the melting and freezing melting point and boiling point of our substance. Since it's water, you guys probably know, we just talked about, water's freezing and melting point is 0 degrees Celsius, and boiling point is 100 degrees Celsius. So we're starting down here at negative 15 degrees Celsius, and we got to get up to 125 degrees Celsius. Okay, so at first, the ice is going to heat up from negative 15 degrees Celsius to 0 degrees Celsius. That's just heating up one substance. Energy going in, heat up a substance. You've done that before. That's using your energy, E or Q, or delta H, equals mass times specific heat times the change in temperature, T2 minus T1. So you do that. Take the mass of the water, or the ice in this case, times the specific heat of the ice, times the second temperature, minus the first temperature. Whoop, and that's backwards. It should be 0 minus negative 15, which actually do the same number. So mathematically it'll work out the same way. It'll be 47.25 joules, but those numbers are wrong for the temperature in there. You get 4,725 joules will be required to heat the ice from negative 15 degrees Celsius to 0 degrees Celsius. Then we're at 0 degrees Celsius, we're at ice's melting point. Now you put the energy into melting the ice from that green part. So that's called the heat of fusion. Fusion means putting things together, but also the energy to break them apart. How much energy it takes to fuse things together is always heat of fusion, heat of melting or boiling or fusing things. It's always in joules per gram. So how much energy it takes per gram of substance. So this is actually much easier. You gotta know, look up or know what the heat of fusion is for a substance. For water, it's 333 joules per gram. So we got 150 grams, so we just take 333 joules times 333 joules per gram times 150 grams, cancels out grams, so we're left with 49,150 joules of energy required to melt the ice. Look how this number compares to this number. Way more energy to melt the ice than it was to heat up the ice. Just be aware. Okay, so now we're at the end of the green part. We've melted all of it. It's all liquid, but still at 0 degrees. Now we got to start heating the liquid water to get it up here, because we are not yet at 125 degrees Celsius. So water will heat from 0 degrees up to 100 degrees Celsius. So it's a 100 degree change, but it's all the same liquid. So we go back to our E equals mc delta T equation, our energy change equation. So now it's 150 grams of water, liquid water. So we use the water specific heat. And then the temperature change of 100 degrees Celsius minus 0 degrees Celsius. And we get that energy output. So that's how much energy it takes to heat the water for 100 degrees. That's the yellow part. Now we're at the boiling point, but it's all still liquid at this point. 100 degrees of liquid water. Next, we're going to boil the water. That'll be this purple part. Okay, so purple part. The heat of vaporization is what's called to boil, to turn into a vapor. So heat of vaporization is vaporizing, turning the liquid into a vapor. Just like heat of fusion was going from a solid to a liquid or liquid to a solid, same thing here. Now this one's going to be 2,260 joules per gram. You might be given these, or you can look them up. It'll be available. So we take 2,260 joules per gram. We have 150 grams. The 2,260 joules per gram times 150 grams. Our grams will cancel. We get 339,000 joules. That's more than all of ours have been before. If I flip back, 62,000, 49,000, 4,000. This one is 339,000. The heat required, the energy required to boil the water is more than, so this purple part is more energy than all three of these parts put together so far. Boiling the energy, separating those particles completely from each other, takes a ton of energy. Whew. Okay, so now we're at the steam part. It's all turned into steam, but it's still at 100 degrees. Our goal is to get to 125 degrees Celsius. But since it's all steam, we just have to heat it up. So we have to go take 150 grams times the specific heat of steam, and then take the change in temperature from what we started at, 100 degrees Celsius, to what we want to get to 125 degrees Celsius. We get our final change of 7,462.5 joules. Great, we're all the way there. Done. Almost. But since we're saying how much energy does it take to get from way down here to way up here, so it's all those pieces together. So we've got to add up the blue part, the green part, the yellow part, the pink part, and the red part. So add all those parts together, and that total answer, 463,450-ish joules, will be your answer. But anything that big, we don't usually put in joules. We put in kilojoules, so you might need to convert it. If you're in my class, at the back of the periodic table, we give you conversion factors for it. So you get about 463 kilojoules as your final answer. Hopefully that makes sense. If you've got questions, write them down, let me know. We can go through them.